Swayam Prabha. Digital India. Educated India.
Okay, welcome everyone. So this is day 3. Um, I hope you are enjoying so far. So today I think we'll accelerate a little bit. We'll go into more details of different machine learning models. And today we'll have Dr. Kamal taking us through one step forward in this course. Um, okay, yeah, thank you.
Okay, thank you, Rohit. So, good morning, everyone. Good to see you back. So, this is day third of the Gyan course, and just I would like before I start, I would like to recap what we did on the first day. We did a lot of things. So, we started with basics of material science. We talked about PSPP relationship, which is processing structure property performance relationship. We talk about different classes of materials, different experimental methods, as well as different computational methods which rely on quantum and classical principles. We discuss about multi-scale modeling, um, the need of programming and different types of programming skills that might be necessary to a certain extent for doing multi-scale modeling and materials informatics. We talked about the parallel and single processor computing, quantum mechanical principles, density functional theory. Um, then we talked about MD, molecular dynamics, classical force fields, statistical ensembles, choosing the right software, continuum mechanics a little bit. We just touched upon this. So now you guys are expert in material science, both experimentally and theoretically. Okay. So let's assume with that assumption, the day 2 would be how to use this experimental as well as theoretical principles to develop databases. And once you have databases, what kind of classical machine learning techniques we can use. So when I say classical machine learning, we are talking about fingerprinting or tabular data sets. So let's get started. So what is AI? At this point, I think I don't need to introduce this huge topic. There's a huge boom in this in our generation, and they say um, this is probably the biggest boom in last 100 or few hundred years. So it's really great time to be alive at this moment, 2025 and so on. There's so many great things happening. So when I say AI, it's basically a generic term which mimics cognitive functions, some part of the brain and so on. A part of this is machine learning, which is dealing with where the number of samples are not too many, so 100, 500 samples data, and that is a case of small data sets. And some of the methods we use, linear regression, I think Rohit must have discussed about that yesterday. Linear regression, random forest, decision trees, Gaussian processes. These are in the domain of machine learning. While this is fine, but we have in last 7 or 8 years, there have been emerged a new technique called deep learning, which is very data hungry. So it requires a lot of data, and it's primarily, if not all of them, are based on neural networks. So this is how our brain and neuron works, and there are several algorithms in neural networks, such as the plain or vanilla or artificial neural network, convolutional neural network, graph neural network, autoencoder, and so on. Okay, and in deep learning, especially for material science, we have 5 types of data. So it can be like chemical formula, aluminum oxide, smile string, like we talked about, maybe you learned from yesterday session. Atomic structures can be coming from molecule, solid protein, text, literature, spectra such as XRD, NMR, and so on, and images such as SEM, STM, STEM, and so on. So one way or other, you are dealing with this domain, okay, in material science at least. And if you want to learn more about this, I will encourage you this papers that we wrote, I think a couple of years ago or 3 years ago, on recent advances in applications of deep learning methods in material science. Over 2 years, it has been cited 500 times. It's an extremely popular article. And the idea is we provide different domains of application of deep learning in material science, different data sets that are associated with those machine learning algorithms and their application areas. So why do we need machine learning? So first of all, we are dealing with multi-scale, multi-fidelity methods like density functional theory, force field, mesoscale, and we want to bridge the gap or kind of connect them. And one of the greatest connector or bridge is the AI methods. So for example, you can take data from DFT, train a machine learning model and run MD with it or force field with it. Take a force field and run a guide experimental design techniques with this and so on. Another thing is in material science, as we saw, there are different types of data like scalar data, like single value, like bulk modulus, band gap, or spectra data such as X-ray diffraction and so on, image data and text data. So the crystal structure, molecular structure, images and spectra and documents, right? And there was an initiative called Material Genome Initiative, which was started by Barack Obama, former President Barack Obama, and the US CHIPS Act by Joe Biden in 2022 really pushed this kind of systematic material design and bridge the gap between scientific research and industry. Because usually what happens, there's a scientific discovery, but to get to industry it takes 10 years or 20 years or maybe never, right? So to lower or narrow this gap, to make this gap narrower, that was the motivation behind this MGI and US CHIPS Act. So AI ML is now considered as a fourth paradigm. What I mean by this? So the first paradigm was empirical science, trial and error kind of thing. You take stone, rub it, and what do you get? Water. No, I'm just kidding. Fire, right? So that's empirical science. Second paradigm is model-based theoretical methods, such as laws of thermodynamics, like first and second law. Third paradigm is computational science, like we talked about DFT, MD, and so on. And the fourth paradigm, especially after 2000s, is predictive analytics or the big data science and machine learning techniques. So these techniques have been applied in many domains of materials classes like superconductors, magnetic materials, thermoelectric materials, carbon-based materials, photoelectric materials, high entropy alloys, porous material, and literally I haven't seen any field which has not adopted AI to a certain extent in material science. So while this was a kind of different areas or different material classes for application of AI, there are different techniques in AI as well. So there is a paper which shows different kind of machine learning techniques. For example, traditional machine learning or conventional machine learning, such as CNN, support vector machine, K nearest neighbor, random forest, and so on. We'll talk about this briefly. And those kind of evolved, but they are still being used, but not that heavily used and until before 2016, 17, 18, along those area. But after that, a new invariant discriminative graph neural network came into play. So this really took off, and you can see it's like really evolving. So like SHANET, CGCNN, Magnet, Align, which we'll talk about, MATFormer, ECN, MAT, and this is just the tip of the iceberg. There are many other models which is not listed here. Okay, so this was GNNs. Now there was also a area of equivariant graph networks such as CDVAE, MACE, Allegro, and so on. Okay, and finally there's another domain area of machine learning such as large language models such as ChatGPT, Atom GPT, Battery GPT, Bio GPT, Astro GPT, whatever you can think of. Now there's like GPT for everything. So and then that was the five kind of different algorithms or methods, you can say. I'm counting at four. I'm sorry. Four kind of techniques of a kind of broader perspective or different methods of machine learning for material science. Now the idea of this is, again, we first design or generate data set, we do high throughput screening, we do computational modeling, and then we do experiment and synthesize. This is usually the forward process. That's how people do different kind of discovery, right? And it can be for AI for predicting material properties, or such as band gap, TC. It can be for AI accelerated DFT calculations. It can be for conditional generation, such as I want this particular behavior generated with this material. And for this, what we need is benchmark, data set, and many other things have evolved. But the goal is the same. to be a kind of god in a way. Like, I want this material, just develop me this material. So like, in if I've seen this old movie thing, they do something like this and something appears. We want something like this eventually. Of course, it has to link with experiments. So we have to close the loop by something called self-driving lab. I think on the 5th day we'll learn about this more. So the idea is we'll do different types of inverse design. We'll talk about that as well, where we basically generate data set. We do some sort of model, like a preliminary model, but also based on that recommendation from that model, actually make some device or make some material and see whether it worked or not, and just fine tune our model, and it's a feedback loop. Keeps on going, right? Just like cooking, you try something, not good, put some more salt or something, it's like this, self-driving cooking, and here's self-driving lab. So there are different types of machine learning techniques. What are those? Supervised machine learning. So in terms of supervised machine learning, and supervised, unsupervised, and reinforcement learning. So supervised machine learning are special classes of machine learning techniques where the labels are defined, right? For example, here is my X and here is my Y, okay? Suppose you do not know Y, but you can still use machine learning, which is crazy in a way, right? Suppose you have only data. What can I do with this? That is called unsupervised machine learning. And we'll learn about that a little bit as well. There are some other techniques we can apply is k-means, principal component analysis, and so on. While in supervised machine learning, we have like support vector machines, neural network, which can be used for classification. So take an image, tell me it's cat or dog, for example. This is a classical example of classification. Regression, such as instead of saying whether it is a cat or dog, I want to say the weight of the cat, for example. This is a number, right? So this can be for regression. And there's also reinforcement learning. So this is especially used for rewarding the desirable actions. It's especially very useful for robotics. So self-driving cars, right? So in a self-driving car, you have a reward function. We have a preliminary model to start with, and then as you are driving the car, the model is still learning and optimizing its weights and getting better and better and better. So this is the idea of reinforcement learning. So in general, we have 3 types of machine learning methods. What are the applications? As I said, it can be used for material property predictions, and this particular field I feel like is really beaten to death. This is the most common area of application of machine learning. So this is a structure predict me like yield strength or thermal conductivity or stress strain curve and so on. It's a very common area of property prediction. Another is design optimizations, like using genetic algorithm to optimize the shape of an airfoil or maximize the lift drag ratio, like when you're designing the blade of a plane and stuff, fall detection. So such as use support vector machine to classify different types of wear in bearing based on vibration data. Also, it can be used for all the car companies or several phone companies when automatically detect the defect and just classify as good versus bad. Predictive maintenance, process control, and so on. Now, the general procedure of machine learning is not that hard to understand. But again, this is not all of the machine learning. Okay, this is like general idea of machine learning. What we have is define a problem. Now, believe me or not, most of the people do not know what problem they are solving, especially in PhD and postdocs. So that is a problem. So first, we should have a clear idea what is the problem you are solving. Are you curing cancer? Are you making better battery? Are you making a better solar cell? What is your problem you are trying to solve? Once you have the problem in hand, according to that problem, according to a sophisticated problem, generate data sets. It's basically, in a way, it's like market research, what you call in economics on financial terms. You do a lot of data collections. Once you have data collection, you put it in front of you and see what are the features that affect that data, right? So that is called feature engineering. And then once you have that features, so then we do different type of algorithm and select what is the best algorithm for this particular application. Is it neural network, random forest, which one? Or sometimes we have something called auto ML. So you just dump all the data, it will figure out what's the machine learning it will require, right? So there are some techniques as well. And then you have the output, and so model selection, you train the model. So you take, for example, 100 samples, you do like 80% for training, 20% for testing, and based on this loss function or the error, in a way, you guide your model to further improve. That's a typical pipeline. And if the model is really good, then you can deploy it. And what I mean by deployment is just make it publicly available. Like ChatGPT is a good example of this, right? It's a model which is serving millions of people. I don't know how many people really find it useful and use it on a daily basis, right? Google search is also a deployed ML model, for example. So as I said, define the problem. And I know this is always not that simple. What is the problem, right? Sometimes it's not that simple. So we have to understand the problem, right? And then once you understand the problem, define the objective. What is the clear objective you want to solve? And the scope. Sometimes we cannot solve all the problems of the world. So narrow down your scope sometimes. This helps. So again, once you have this, sometimes you need supervised or unsupervised or reinforcement learning, and sometimes a combination of these. Okay. So define the problem, collect the data. In terms of collecting the data, make sure there is a diverse amount of data, right? So suppose you are collecting data which is a very constant kind of data. It's not diverse. For example, I want to weigh a cat, okay? Weigh a cat, and you have only 2 cats you have seen in your life. So you will always say the cat weight is only this. But if you have really a diverse data, then you get better models. And also, if you have you want to make a model of cat's weight, but instead you are measuring its length, so that model will never predict the cat weight correctly, right? So that's called garbage in, garbage out. So make sure you understand what's going on. And 50%, if not more, the problem is about good data. And most of the companies like ChatGPT and Google and Facebook, they pay huge amount of money just for engineers to clean up the data. That is their whole-time job, clean up the data. So once you have the objective, once you have a decent amount of data, you will understand where the data is coming from, you collect it, you store it in a way which is accessible. So remember, on the first day, we are doing a notebook analyzing DFT data set. We did pandas data frame. It was so easy. Pip install blah, 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 PD data frame, blah, blah, blah. And here is an entire 80,000 materials worth 7 years of work in one command. How easy was it, right? So we want the data be in that kind of format. If you want to be really do machine learning or be useful to the community, if your motivation to serve the community of material science, it should be very nicely packaged. And ask yourself, can I use it conveniently? If I can use it personally very easily, then others can probably use it too, right? So data storage, what are the techniques you might need, and what kind of methods you are storing, where are you storing, like Figshare, Kaggle, Zenodo, GitHub. These are different platforms for storing data, or which is publicly available, or Google Drive and so on. Sometimes we need version control. Sometimes we need something like how many times it was downloaded and stuff, So those kind of analytics to guide our funding process and so on. That's why you have to be aware like which platform to choose. So the first thing, once you have collected data, is called EDA, or exploratory data analysis. What is that? In layman word, just plot the data in different way you can think of. That's what it is. So once you do that, you'll understand what are the bounds of data, right? So as I said, the weight of the cat, right? If you have only 2 cats and it's like, I don't know, what's the weight of a typical cat? What's the weight of a typical cat? Huh? How many? 2 kg? 2 kg, right? Suppose you have one cat 2 kg, one cat 2.5 kg, right? And you make a histogram, right? So only 2 and 2.5, there's a 1 bar plot, right? So if you want to have a model that can predict weight of a cat with 10 kg, probably this will never work. Do you know what I'm saying? That's why you need, once you have diverse data and you have plotted the range of that data, you can actually say, okay, this is my confidence range in a way, and this will work well here. So that's why we have to do EDA, exploratory data analysis. And there are many, many ways. We did the bar plot the other day, so I'm not going to do that today. But there are many other ways. One of them is called TSNE, which I used to like a lot, but now it has been UMAP is pretty popular. So what is it? I'll explain a little bit. So suppose you have let's stick with the cat example. I don't know how I come with the cat example, but just let's stick with this. We have the cat weight, cat age, cat's length, cat's eye color, cat, what else we can think of? Fur color, right? So you can make all this something called descriptors of a cat. And what's the use of this descriptor? Distinguish one cat from other cat, right? Now you have, suppose you have come with 1,000 such descriptor. Assume I can maximally come with 8, right? Suppose we have 1,000 and we have for 1,000 cats. So how much? What's the size of a matrix? 1,000 cats and by 1,000 descriptors. Now there is no way we can plot this. Human mind is limited to 2 or 3 dimensions usually, right? So what we can do is somehow, very smart way, convert into 2 dimension, and that is what is called t-SNE, t-distributed stochastic neighbor analysis. Okay, so what it does is it takes this huge data and without losing a lot of data, find in a data in 2 columns, let's x and y, so that the information is still kind of preserved, right? And there are other models nowadays very popular is UMAP. So you can see here, you'll be surprised. What it is archive, right? Archive preprint. We put a lot of papers there. So there are about 1.5 million papers starting from 1986 or something. So one of our project like Chem NLP, what we did, we took all the and in archive there are several categories, if you have seen, like condensed matter and all these kind of things are there. So we took only condensed matter category, took all the titles and abstract, okay, and suppose, I'm just saying in a layman word, but suppose for each word I give the index of that word in a dictionary. So suppose in a dictionary we have 1,000 words and the cat is at 1200th place. So if the cat occurs in the abstract or title, that will be replaced by 1200, and we convert all the title and abstract in that numbered category, okay, and then we convert wrap this in 2 dimension, and that what it shows you. It shows you that if of all those, I think 100,000 papers, how many of them, like condensed matter, material science, are the pink one. They start to make clusters. Because why? Because there are certain number of words like structure property and stuff like this occur over and over. So they're going to cluster here. So that's one way of visualizing your data. Another way is like crystal system, 7 crystal system and so on. You can visualize it. So yeah, first visualize the data and then we apply machine learning techniques. Now there are many machine learning techniques. Which one should I use? So the first one to start with is linear regression. So linear regression, we have done a lot of Excel plotting, right? You have X and Y plot and there's a small display R square and display equation and stuff, remember? So what we do is, what happens there, you have X data, which is the, what do you call it, independent variable, right? And Y is a dependent variable. And then you basically try to fit a straight line, like Y equals to theta 1, theta 2, X, and then make something called residual sum of square, which is yi each point minus beta naught. I don't know what's the value of beta naught, just guess it, like 0.5 or something, and beta 1, and keep it minimizing such that it fits all the points approximately. So this is your first machine learning. The good thing is the beta naught and beta 1 represent some physical meaning, the slope and intercept, right? So that is called interpretability of models, okay? So linear regression is a very interpretable model in that way. Now this is for 1 dimension. You can do it for many dimensions. Remember we talked about the cat characteristics? We can have one for each of them, each column. So that will be a linear regression model. Now sometimes we don't need actual data, but we need probability, right? So we want just chance. So for that there's a logistic regression, which is used for classification. So you can see 1 over 1 plus e to the minus x mu over s and stuff. So this is specially used for classification. Now this is fine, but these are rarely used for machine learning, like almost never used for machine learning tasks. One of the most popular machine learning algorithm is tree based. So it is based on if and else statement and if and then statement. So like for example, you want to predict age of a cat or age of a man, whether it's less than 40, greater than 40, spent a lot of money last week or not spent a lot of money last week, or has kids or not has kids. If you have kids and you have low spender, then this is this category and so on, So you can classify and based on this, there's something called Gini impurity function. So you can convert this category behavior in Gini impurity and kind of train the model to predict what happens if I give a new data, what will be the value. So this is called tree-based model. There are different type of tree-based model, such as decision trees, random forest, gradient boosting, ADA boosting, many algorithms are there. Now, the next one is standard neural network. So for example, we have two dots here, two green dots, cute little dots, x1 and x2. Let's assume this is molybdenum and sulfur atom, okay? And Y here is the band gap of that system. Now, you can use something like density functional theory or perform an experiment to establish the relationship between the input and output. But let's assume we don't know any such thing. What we'll do is we'll have a magic black box, which we call hidden layer, and connect everything to everything in a way that we can have a predictive model. Okay? So what happens is, first you have to give some descriptor, again to distinguish one dot from other dot, right? So this X could be for electronegativity of the atom, atomic number of an atom, what else? Boiling point of an atom, heat of vaporization, period number, group number, think of several things. In that way, you can discriminate or distinguish one atom from another. So that can be something called X. Now this X cannot itself learn anything, okay? So what we do is this X, we multiply with a vector or a matrix, which we call W, weight matrix, okay? And then you add, like shift this up and down and stuff. This is called bias term, okay? So you take this X, multiply by W, add a bias term, and then there could be non-linearity in the data set. Not everything is linear. To capture that, we need a non-linear function called sigma. This can be a hyperbolic function, tan hyperbolic, sine hyperbolic, and so on. So without this non-linearity, all the non-linear networks are garbage. So it's very important to choose non-linearity very, very well. Okay. So once you have this for lth layer, one hidden layer. Now you can have many of such layers. And then suppose you have an initial guess of this weight matrix and bias matrix, and then you get the y tilde, which is the output, and then you know the actual target of band gap. Then you again subtract those two numbers and you get the error. This error now is a function of your weight matrix and bias values. Now I want to vary this in such a way this my error is minimized. This is called gradient descent, where we are trying to minimize the cost with respect to the weight and biases. Now there are many ways to do gradient descent. One of the most popular one is backpropagation. And what is backpropagation? We have seen in the calculus class, right? So if you have the chain rule and stuff, it makes the training very fast. So this is a typical standard neural network architecture. And if you want to be a good materials informatics or machine learning person, always think about what's going with the cost function. A good machine learning person knows, number one, where is the data coming from, how good or bad is the data, and second, how to manipulate the cost function. Okay, so these two things. If you are in an interview and somebody is talking about machine learning, just talk about these two terms I told you. They'll be very impressed with you. Okay, so what are those? Data set quality, data set diversity, and the cost function. All right. So this is standard neural network. Now you can see this everything is connected to everything here in this particular picture. So if we have some large amount of data, like thousands of cats, or you can think of pixel images like photograph, right? A photograph usually have like, I don't know, 500 by 500 pixel, depends on the resolution of the image. So suppose you want to have classify the cat, then you have to kind of connect all these points to all of these points on the neural network, and it becomes very cumbersome. Huge number of parameters. Some smart people think of something called convolutional neural network. What they did is they think of this learnable parameter. Here it's 1, 0 and so on, but it's not actually 1, 0. It can be variable numbers. So what they did, instead of connecting everything to everything, let's assume this convolve over blocks of those pixels. Okay, and then kind of do a sum pooling or average pooling or minimum pooling or max pooling, and from there we establish again standard neural network, like predict with a cat or dog and so on. So in this way we kind of lower the cost of the machine learning, and this is especially very useful for images. And this is fine, but unfortunately it doesn't work for material science too much, like atomic structure, because atomic structure like molybdenum, sulfur or silicon is not like on a grid. Unfortunately, we think we are in a grid, but we are not really on a grid. There are some chairs missing, somebody here is missing, all this. Actually, this kind of grid, actually like it, but it can be non-grid too, right? So what to deal with that? How to deal with this? So this is the concept of graph. Now, what is a graph? It's a collection of vertices or nodes and edges. These two things, nodes and edges. So here in this class, you each of them are node, and the connecting point is edges, or what's a better word of edges, like bonds or something like this, right? So here you can consider a graph where 1, 2, 3, 4, 5, 6, all these are nodes, and the black line are the edges, the connecting points. Here 1 is connected to 2, 1 is not connected to 3, 1 is connected to 5, 1 is not connected to 6, 1 is connected to itself sometimes, right? So you can store this information in something called adjacency matrix. So in this matrix, you can see 1 is connected to 1, 1 is connected to 2, 1 is not connected to 3, 1 is not connected to 4, 1 is connected to 5, 1 is not connected to 6. And in this way, you can make a 1, 0 kind of function, 1, 0 kind of matrix to kind of capture the real space information. Now, it can be 1 and 0, or it can be actual like bond length, right? Or the number of tweets we have if we are Twitter and something like this, right? So it can represent different kind of data in a way. So once you have this adjacency matrix, and there are many different type of graphs. Let's not go there. Let's not go there. But suppose we have this adjacency matrix, we calculate the degree of the node. This is the row-wise sum. That's all it is, and just divide every row by the degree just to make numerical stability. And then what we do is similar to the first neural network. We have like atomic number of each atom. We as a what's this one called? Column matrix, right? One like column, like column matrix, right? So we have a 1 column matrix for each atomic number here, and this is chemistry information, and the structure information is in the adjacency matrix, right? And then you take that and multiply by a learned neighbor weight matrix and a bias term, okay? And then you do it many times, okay? And then you want to predict like band gap or something like this, right? And you try to optimize the weights and biases so that your error is minimized. Loss function, remember we talked about this, minimize the loss function. And then we do it very efficiently on a graphical processing unit, GPU. This happens very fast on GPU than CPU. So that's the idea of graph neural network. Now there are other models such as autoencoders. What are those? Suppose you have one of the applications of this for images. So you take all the cat's images, right, and which is like 256 by 256. Now you want to condense into a form which is like 256 by 256 is how many numbers? 6,000, I don't know, something like this, right? It's a huge dimension. You want to crunch it to something like 100 dimension, okay? So this crunching is called encoding, all right? And if you take this crunch number and find a model that can take this crunch information and again represent cat or some image, that's called decrunching or decoding. This encoding and decoding, this is the idea of autoencoders. And why do we need this? So suppose, first of all, to reduce the dimension. Remember we talked about the first many dimension, crunch dimension. It's used for that. It's also used for generating new data sets. Suppose we took all the possible images in the world and condensed it to 1,000 dimension. So and now you want to generate a new face. So I was talking yesterday, like there is a website called thispersondoesn'texist.com. Okay, so anytime you click there, what happens? A random number is generated, and from the random number, decode it to a face, and of course that face hopefully doesn't exist, right? So that's what happens in decoding process. So this is called autoencoder. Now this is fine, but a more realistic model, which kind of really more superior in terms of performance, is diffusion model, and which is based on diffusion processes. So what happens here? Suppose you have an image. Now instead of directly doing a condensing to encoding, we do it gradually, like add noise, and make it complete noise. Now have a model which can take small, which can denoise, and get the cat back. So this model of forward diffusion and backward diffusion, if you can learn this, what will happen is now you can generate any images. You have learned the hidden dimension of all the images. And that's what happened in something like ChatGPT. When you write generate me a a cat with a hat of or something like this. So you take that text, convert into number, put into that dimension, and gradually denoise it to make your beautiful image, right? So that's what happened this with the diffusion model. Very popular for images. Now the final one is transformers, which is very popular nowadays, and all the GPT, the T in GPT is transformer. So it's called generative pre-trained transformer model. So what happens here, let me explain this with an example. There is a question, hi, how are you? Okay, and the answer is, I am fine, right? Now, suppose you have thousands of such questions, like what are the other questions? Hi, how are you? How are you doing? I don't know. Where are you going? And stuff like this. You make a question like this and your responses. Now, what happens in a model like this, it can, remember we talked about the words can be tokenized and can be given numbers based on dictionary index, right? So suppose we give hi, I don't know what part of the dictionary would be, maybe middle, like suppose there are 200,000, maybe it's 100,000, right? And how is maybe 199,000 or something like this. We give the index for this. Similarly, I'm fine is also we give index to this. Now we make a model that can map this x and this y in a way. If we can do this, then we can have a model. If I have a new question, like instead of asking hi, how are you, why are you? I mean, I shouldn't ask why are you, but suppose I ask this question. So it will take this question, make into a token, and again kind of answer the question because it has the model trained on the pre-trained data, right? So there are a lot of, again, informations like key, query, variable, and stuff like this. I won't go too much in details of this, but this is very, very popular model. I think this is one of the most highly cited papers. It came from Google. I think just 7 years it was cited like 500,000 times or 200,000 times. Can you imagine 200,000 citations for one paper? Imagine. This is that popular paper. And there is no journal, it's just an archive. No Nature, no this, that, just archive. So if your work is really powerful, it can really change the world. This is kind of example of this. So this is transformer architecture. Now we talked about model training. So in model training, what we do is, suppose you have 100 images or 100 data, SEM images or something like this. You want to train on 80% and test on 20% in your model because you're not going to generate new data for testing. And then sometimes you don't want to do only one time 80 and 20 split. You do it multiple times. So 80-20 split, randomly shuffle it, then another 80-20 split, randomly shuffle it, do it 5 times, and then get a metric. So that part is called cross-validation. Okay? And then train the model. What I mean by train the model? Adjusting the parameter like weights and biases. And then hyperparameter tuning. So hyperparameter tunings are like I was talking about in the previous slide. How many hidden layers should I take? How many neurons should I take? So these are called hyperparameters. So in a way, these are so many controlling behaviors, controlling variables, right? And most of these things can be easily automated nowadays. There are something like scikit-learn packages, auto ML packages, especially for fingerprint or descriptor-based models. You can just dump the data and just it will do everything for you, like all the training, test split, all the plotting, everything, and stuff like this. And I don't know how to emphasize more and more about this loss function. So I want you to have at least one thing. If you learn from this entire class, it would be loss function. Okay, how you craft your loss function is very, very important. So one of them is gradient descent is a fundamental optimization. So gradient basically, if you go from one parameter set to other parameter set, how did it vary? That gradient is important. Is varying fast, it's varying slow, right? So and there are different type of gradient descent algorithm like batch gradient descent, mini batch, stochastic gradient descent. So sometimes we don't have enough memory in our RAM to fit all of the model data. So what we do is do a batch, like batch of 20. Batch of 20 went there, train the model, output. Another set of 20, train the model, output. So this is called mini batch. Gradient descent with momentum. Now this sounds like physics kind of thing, momentum, right? But it's actually, what it does is accumulates a velocity vector in direction of persistent reduction in the cost function. So you try to find out what is a direction in which my loss function is decreasing more and more. And again, you don't have to code it up. It's all there in libraries like this. And then once you can find out, then you can vary like learning rate or batch size or some parameter to kind of get more and better function. And there are a lot of research like RMS prop, ADAM. ADAM is very popular function like adaptive momentum estimation, and there's also ADAM-W. So ADAM combines the idea of momentum and RMS prop, root mean square propagation for ADA-grad. So again, these are all jargons, but usually if you start with an example, these things are much easier. So during the hands-on session, we'll try to do that. Okay, so objective functions, and if you have done some sort of force field training and stuff, some of you I think have done force field training for MD. So you see sometimes you have to change the weights of the parameters manually, right? So those are very important, and that's why it's important to understand loss functions. So suppose an example would be, suppose you are making a force field and you have energy and forces, but your loss function is being guided only by energies. There's a lot of contribution of loss from energy, so the model is never optimizing forces. So what we'll do is take the weight of the energy term, make it like maybe half or 10 times lower, so that the total loss from each contribution is almost the same, right? And that's how you guide the loss function. And this is just an example. Now, once you have done the model training, we have different type of metrics. Like for classification, there are metrics like accuracy, precision, recall. For regression, we have R square, mean absolute error, root mean square error. Pretty sure you have learned some of these in statistics and stuff, right? And always calculate baseline. So what is a baseline? Suppose we have, again, let's go with the weight of the cat, okay? But suppose we have 100 cat weights, and we have 80 cat in the training and 20 cat in the testing, right? And suppose I ask you, what's the weight of this random cat? And I don't know any model. And what I have is just training data. What will you do? Any guess? Average, you're right. So just take the average and I'll do a guess game. So that guess game is called baseline, okay? So your machine learning model should be better, must be better than the guess of average guess. If it's not, there's no point of doing machine learning. Does it make sense? So always have a good idea what is your baseline, right? So where were we? So for classification, it's usually, unless there's a class imbalance, is U1 over N. So if you have a cat versus dog image, what's the classification baseline? 50%. That's all, right? So for regression, as we said, the average, the MAD or mean absolute deviation and stuff. And then we have to know about cross-validation, compare and these are some of the metrics. Again, these are all coded up. You don't have to write the code for calculating mean absolute error and stuff like this. So, but it's important to understand the metrics. Suppose you want to classify a cat versus dog image and you are using mean absolute error, then it will not work because that is not what is meant for. So you have to, for classification, you have to use precision or recall metrics. And this is what I was talking about. Sometimes we have a lot of parameters, then the model becomes very complex, the error goes down, but the model is becoming too complex and it's hard to train. So you have to find something like error is also low and model also not that complex. Sweet spot, the optimum value. And this takes a lot of trial and error, and this is called bias variance trade-off. Model deployment, this is only for developers. Suppose you have made the model, then how do you share with the world? So you share with something called Flask, Django, Fast API. These are some resources, and these are all in Python, I feel like, and most of them at least, or and host in Google Cloud. You have to pay money for this, and so on. And again, you have continuous testing. You monitor the job and so on. It's called cron job, which basically tests the model every minute. You set it every minute or every hour or every day, every month, and automatically test it and stuff. So we have this for jarvis.nis.gov. Every few nights, it tests a lot of things, all the codes, all the data and stuff, and anything breaks down, it emails not me, but all the people who do this painful job of maintaining it. So we have to do this if you want to do a long-term project. There's different software libraries for machine learning. So one of the most popular is scikit-learn, and it can give you classification, regression, clustering, and so on. Other model is PyTorch. It's a model from Facebook/Meta, And there are other models like TensorFlow, JAX, Scikit-Image, OpenCV, Pillow, Hugging Face, and so on. We'll talk about this a little bit later. If you want to know again more about this AI ML for materials, so this is the first paper I would recommend. This is especially from materials modeling, called From DF2 to Machine Learning, Recent Approaches to Material Science Review. And this is one paper. The second paper that I am the first author, and because I'm the first author, I'm going to promote it more, right? So this is also a good paper to read. There's a book called AI for Science. So I also wrote a book chapter on this. So you can take a look on this. And there's also a book called Materials Informatics, and so on. So again, in this paper, recent advances, there is a table like this called databases. Okay, and this what is the database name, how many data points are there, where the link is, where the reference is. We have given all the information there. And this is quite old, like 5-year-old, but you can see there are not many, but there are certain database coming from Indian institutions as well, and hopefully more database. I have seen a lot of interest. I was talking to Rohit and other researchers. They are building a lot of good database, which is really good for this country, right? So if you want to establish yourself in machine learning, have your own database, which is good one, and which is being used by others especially, right? And a lot of US databases, a lot of Europe databases, and you can see here there was less. Suddenly there are so many now. It's too many now for material science databases. And there are different softwares like Align, we'll talk about Annie. These are again different type of methods, like how to establish the structure property relationship we talked about. So there are different software packages, MapMiner, and we'll touch upon some of these as well. So I think we talked about this before as well, but yeah, we're going to use Jarvis database. And just to let you know, we have around 200,000 users. So hopefully you'll get plus 50 users from you guys. So we have almost every country kind of using it right now, especially US, China, India, and it's downloaded more than 1 million times. So it's not like, I don't know, YouTube viewers and stuff, but something like that, how many times it downloaded and stuff. And there are different types of databases for density functional theory, force field, natural language processing, direct air capture. There are many, many flavors to this. You don't have to know all of that, but I'm taking this opportunity to advertise my database, that's all. So we had talked about this Jarvis Tools Notebooks collection. We are doing the exercise, and that's a good way to start. I think somebody asked me what's a good way to start with these kind of things. So that's one way. Another way is if you go to jarvis.nist.gov/events, we organize several workshops, and we have a lot of recorded videos for really fantastic speakers. So you can learn from them as well, just on your own time. Okay, so now we will get into the feature engineering part, or something called descriptor. Now, there are, again, the problem. What is the problem we are trying to solve? We are trying to establish the structure property relationship and do it more accurately. And scientists all over the world have tried in different ways to characterize or differentiate one material from another. For example, element descriptors like atomic number. We'll talk about MACPI, Coulomb matrix, Ewald matrix, sign matrix, MBTR, SOAP, CFID, CISO. We'll touch upon maybe only few of them. Okay. So, and there are libraries like DScribe, MapMiner, which is a collection of all these kind of different fingerprint library. One good example is chemical fractions. Suppose you have compound like lithium hydrogen, lithium fluoride, beryllium oxide, boron nitride. Suppose these suppose your what's the x-axis, what is called headers. Header are the elements, hydrogen, lithium, and so on up to whatever 100 numbers. So if lithium and hydrogen, you will have a hydrogen column here, one here, but all others are 0, right? That's the fingerprint of lithium hydride chemistry. Similarly, we can do it for any compound, right? So this is called chemical fraction descriptors. And you can, to make it normalize, you can just divide by the total number of atoms, right? Then it becomes a fraction. And then suppose you have a lot of data from chemistry and you want to predict some property, then you convert this chemical formula in that format. Use one of the model like scikit-learn or linear regression or random forest. Do test split, train on 80%, test on 20%, and see which of the model is better or whether it's working or not. Calculate the performance of the matrix. But is this part clear? Like, how do we convert chemistry into numbers? This has to be clear. If not, then there's no point going forward. If you have any questions, ask now. Yeah, this part is clear. That's good. So another more sophisticated descriptors are like, instead of in addition to having like atomic number, we can have like periodic Mendeleev number, atomic weight, melting temperature. So this group of scientists, Logan and stuff, they really thought of any possible thing you can think of. Like, you know, they go to periodic table and they have all the small numbers and stuff, atomic weight, boiling points. They took all of that and kind of make it a table. And they say anytime there's a compound, it will convert into this fingerprint, and they can do machine learning with this. And this you can see is 1,000, 1,000 times over whatever few number of years, just for this idea, because at that time it's very, very popular. So this was chemistry, but how about structure? So one way to do this is using something called radial distribution function. I think one of the hands-on session we did plot a radial distribution function, right? So we can take a crystal structure and do a radial distribution function from 0 to 10 angstrom with 0.1 angstrom bin, 100 numbers. So those are structural features. Now these global features, you can also do something called partial radial distribution. So instead of doing a global one, you will do for each atom type, for hydrogen RDF based RDF, lithium based RDF. So it's called partial RDF for all the atomic number, all the atomic species. Again, it becomes very cumbersome, but some people do that. Another way to do is called Coulomb matrix. So you take, suppose this molecule, I think it's CH3OH, what is methanol, right? Yeah. So what we do is we calculate this matrix called Mij, where Z is atomic number, and for if it's the same, the diagonal component is Zi square almost, and if not, then it's Zi Zj over Rij, which is the bond distance, right? Q1 Q2 over R kind of thing. So you can get that. That's also representative of that particular molecule or material. Now this becomes very challenging if you have thousands of atoms. Then a matrix becomes really huge, and also sometimes difficult when you have periodic boundary conditions and stuff. Another descriptor is something I proposed in 2017, is CFIT descriptor called classical force field inquiry descriptor. So here we take the chemistry fingerprint. Remember we did the atomic number, boiling point, all these things. So suppose you have molybdenum sulfur, and then there's one fingerprint, lithium fluoride, there's one fingerprint. We got the average chemical descriptor. We took the radial distribution function, right? We did plot that. We did the angle distribution function, like the angles, how would they vary. Most of them here is 109 degree, right? In a diamond structure, you know, 109 degree the angle. And then the dihedral is around 60, right? So you take all this and pair it. It becomes one, and you also have something like charge distribution around for each atom from your POTCAR file and stuff. If you sum it up, it becomes 1500 such descriptors, 1500 such descriptors. And then you take this and you can, that's one way, and we found this kind of model works pretty well because it has a lot of this information. There, please.
If you go for the angle part, how do you calculate the angle? I was just
Dihedral angle.
If you're going for the angle, okay, you choose one atom, and after that you're choosing one atom, like you need a triplet.
Yeah.
If I calculate the angle, how you are moving, like if there are too many atoms over there, and how you are just counting the angle?
Yeah, so suppose this is my atom I, J, K, right? So I calculate Rij vector, Rik vector, and this is just Rij, what is the dot of that, Rik, and mod of Rij, Rik. I think, please correct me if I'm wrong. And the cos inverse of this number. This is your angle.
My question is about the class of J and K. How do you choose the J?
Yeah. So first, suppose you have a periodic boundary condition. So you take an atom and you set a cutoff like 2 angstrom or 5 angstrom, and between that sphere, whatever atom is there, you start doing this, right? And you start adding to an array. Like there's a huge array, angles or something, and keep adding this number, and then you do a histogram of that between 0 to 180 degree. That's your angle distribution function. And these are all codes available. It's not a big deal. This is super straightforward. Same with dihedral. So here instead of having Rij, you have Ri, 4 body basically. You can calculate that as well. But again, it becomes sometimes very expensive. Sorry, did it make sense? No.
I will ask later.
Okay, yeah, sure, please. I can show. So there are many other types of descriptor which we will not have time to go. One of the most popular for force field is Baylor-Porinalo. So here we have something called, what is called Gaussian function, but there is a special term for this, G function. I forget the name of this. But you take for each atom, remember, so Rij, the ith atom, the distance from all within the cutoff, Rij, minus the origin, let's call it 0 for now, and you square that, and then you have a decaying function called Fc, like a function which will smoothen up. We don't want actual number, but actually should smooth it out. There are some mathematical stuff like Fc here is cos of Rij over Rc and stuff, within the cutoff or outside the cutoff is all 0. So this is called G function, and this is very popular for making machine learning force field. Another is Agni. So this is also Rohit is one of the developers of this. So and there's other like bispectrum, Zernick, and there are many other types of descriptor as well. Now during our hands-on session, we'll try to compare this for compare the CFIT descriptor, the MACPy descriptor, and the element fraction for a training task. We'll try to do that in the hands-on session, and we will see which one is better or worse in terms of speed, in terms of performance, and so on, just for a toy model. So MatMiner is one of the models, one of the project which kind of have all of that. And actually, yeah, after this we'll switch to maybe take a break, then we'll start doing this hands-on session. Yeah, but before this, any questions? Yes.
For graph-based does the graph has to mimic the original molecular structure, or it can be different from the original molecular structure?
What do you mean mimic here?
Mimic means like, let's say I'm taking a benzene, and I'm
Graph, yeah, graph should look like benzene, yeah, because like suppose if you have benzene, then right, so this is my nodes, and this is like I'll give the coordinate x, y, z of this, and these are my 6 nodes and how they are connected. So these connected to this and so on. So when I say look like this, when you plot the graph here, of course it look like the graph, but it's just like it has condensed form of all the connectivity information. But yeah, it will look, you can plot it too. And it becomes difficult, especially if you have like periodic boundary condition.
Yes,
It looks very ugly.
yes, not even clean.
Not even clean, yes.
It looks like, I couldn't even
Yeah, there is, what's the name of the, Network X. That's the package. You might have seen this, right? So this is a way to plot the graphs. But again, it doesn't make me happy or anyone happy. It looks very ugly for periodic boundary condition materials, solid materials. Yeah, good question.
double edges of there.
Yeah, it's always because there are multiple copies. Although we specify the cutoff, there are many copies of one atom is connected to many atoms and so on. And yeah, it looks too many connectivity. So sometimes what I do is just decrease the cutoff, and then it looks slightly prettier, kind of.
If you increase the superlattice size, that's way better compared to the just decreasing the quantity.
Can you please repeat a superlattice?
If you increase the superlattice size, whatever you're trying to do,
Yeah, you can have infinite cell, but remember we are working locally, right, within certain cutoff for each atom, and then that's why graphs are called permutationally invariant. What's the other? There are 3 invariants: translationally invariant. What's the other one? Rotationally invariant, right? So what it means by translationally invariant is it doesn't matter how big supercell you make, the graph characteristic will be the same. It's like inherently comes from the graph theory.
because we had a problem with the periodic boundary condition and
Yes.
applying the cutoff. That's why they increase the lattice size.
Yeah. So what we do is like we make large enough cell, right, and then start doing the cutoff thing. So at least you have to have like, I don't know, 5 angstrom cell. If not, make a supercell or make an image. You don't have to actually make the supercell, but you can calculate what will be the contribution of that atom in the next cell. And it's a matrix multiplication after this. So remember the other day we made a graph, remember, using DGL? I don't know how many of you remember. So that's what it does for supercell as well. And it works very locally for each atom wise. So it can capture all the environment information and so on.
So the R code is just to identify which atoms are connected to the center atom, right?
yeah, and kind of lower the computational cost, because everything will be connected to everything. That's too much.
I have one general question.
Sure.
Like, let's say we generate a database
Mhm.
from our calculations.
Mhm.
So, what is it a good idea to share it fix here, or just host a website and share it to the world?
Mm.
Can
I
we do
mean,
both?
first thing, I mean, as practical, pragmatic idea, take all the juice out first. You should make a lot of papers and whatever you want to do with this as much as possible. And then once you do this process, then you can share it. I mean, people can always think of different ways to do this, but at least my idea is have 1 or 2 papers before you make it public. So that's one kind of advice in a way. Yeah. But I personally believe I give the data whatever I generate, because later I can find myself. Else I myself cannot find my data after 5 years. Leave even 5, even 1 year, sometimes I can't find my own data. It's good to share publicly.
Even tools.
No, it's from Jarvis tools or something. Yeah, you give a postcard or atomic structure, it calculates this. No DFT needed. You can do for any material. Once you have a crystal structure, you can calculate. Yeah, it's very generic. Yes. Which one was this figure? This one? Okay. Here it will give you the bond distances, right? So how many bond lengths are there on the first neighbor, second neighbor, third neighbor? What's the bond distance? That's all it gives you. That's also in a what do you call in a cylinder, no, not cylindrically, spherical way. So it loses angle information and stuff. But there's only bond distance information. Please, yeah. AI for science. Pretty nice book. It says like for astronomy and biology and political science. I don't know how many things are there. Please.
So when we are making a graph out of a crystal structure, let's say, so we are storing the atomic features in the nodes, right?
Mhm.
We are storing the bond features in the
Edges.
So what do you mean by bond features? Like, it is just a distance between two atoms, right?
Yes.
So it is just a float or some kind of vector?
Just a float. Just a float, but it can be directional, because sometimes if you want to calculate Rij vector, remember for angle and stuff, so we make directed graph. So we store in a way that Rij and Ji are not same. And also, if I understand your question correctly, it's not only the bond length, you can have multiple things. For example, sometimes you can have like Lennard-Jones parameter. That can be a descriptor of bonds. It can be tight binding parameters, hopping parameters. It can be, yeah, there can be many things, but bond distance is very common.
Anything that deals with two atoms.
Exactly. And I honestly believe we have not explored everything. There are much room in thinking what else can we do. So young people like you have the should come with the ideas and try it out. Yeah, so while it's doing this, let me briefly mention that if you go again to the jarvis.nis.gov and click on tutorials, click on the Jarvis Tools notebooks, and slightly scroll down, there is something called slides. So I have put my slides here. Okay, so click on open the slides, and this is the lecture I'm giving you for last few days, or today as well, if you want it. Yeah. I should leave it somewhere. So how many of you guys have done machine learning before, like for research or something? Please raise your hand. That's pretty good. Yeah.
Reconstruction, like
Right. Okay. Let me. I was too fast. So let me point out to a project we have called Atom Vision. Since we have some time, I'll show you this paper. So in this paper, we have different type of machine learning framework, especially for images. So we have like CNN, UNet, super resolution GAN, and one of them was defect detection, like this, where their defects are. And there we are using something called semantic segmentation model, which is basically sort of UNet kind of model. So it's, instead of doing global image classification, they do pixel-wise classification. And if you can somehow learn how to do pixel-wise classification, then you can classify defects, identify defect, and so on.
so this is not an order encoder based model.
No, it's like it's a CNN, a UNet kind of model. UNet is basically, do I have an image here? Let me see. Yeah, this kind of model where you have a model convert to a small bottleneck layer and then convert it back, and we do this for pixels, pixel wise for each pixel. And there is a software, very nice software called Semantic PyTorch or something. Semantic segmentation. PyTorch. I can type. Segmentation models. I think it's this one. Yeah, you can see 10,000 stars. By the way, if you don't know what is stars and stuff, this is like Facebook likes kind of thing. Very good thing if you have a lot of stars. So this model can be used for, they have like UNet, UNet++, so many other models are there. But I think in that paper we used UNet model for pixel-wise classification. So this is like global classification, whether this is hexagonal or tetragonal lattice. This is global classification, pixel-wise classification. So this global classification, you can convert to a graph as well. So because you can consider where the node intensity is there. This is node and others are edges. You can have super resolution. Sometimes we can have, archive has very blurred images, right? Have you seen this 1980s microscopy images? 1990s, very blurred, noiseful images. So we trained a model that we generate the synthetic data set, add a lot of noise to it, make it look really, really bad, and then train a model that can take that and give good images. This is called super resolution. And we tested this model on some of the archive data set. So this can be used. I mean, nowadays all the phones have it, all the Google phone and everything. Remember, you can I think Google phone has it. You can remove some people or add some people very easily. Those are all using some super resolution or something. Yeah, this is like low resolution to high resolution mapping and stuff. And it can be used for, I forget what is this for. It's been a while. Like TEM images, HRTEM images, and so on. But yeah, at that time, UNet was pretty popular. But nowadays, people have moved on to diffusion models more. Yeah, reinforcement learning is not like I guess it is a different type of learning, but you basically have a score function, which kind of interacts with the environment and updates the parameters and stuff. So it's like a strategy kind of thing. Yeah, it's like a loop, learning loop kind of thing. It's not just train the model and done. No, it will keep training. So that's reinforcement. Very useful for robotics. So I think this is, let me search CO2. No pop-up. Yes, this guy. Graph neural network predicting metal organic framework CO2 capture, right? So in this paper, we took the HMOF data set and also, what was the other one? Yeah, hypothetical MOF data set and also something called core MOF data set. So there we had, let me see if I have the schematic or something. Maybe not. So we have the MOF like this, and we have the corresponding CO2 capture data at 1.5 bar or something, I forget. That's my Y. We convert the crystals to graph, train the model. Now if a new crystal structure, new MOF structure, will predict the CO2 capture. That's it. And we actually validated it using experiment. It works very nicely. for new MOFs. Okay.